Hi. Okay. So, on today's agenda, we are going to prove the inverse function theorem for... We're going to prove it for analytic functions. Before we do that, real quick, I just wanted to make a note. Actually, this note, which is cut off, about this theorem. So this theorem we have in the differentiability section. It states that if we have a locally convex domain for a differentiable function, and we have two contours which are homotopic, then the integrals are identical. Actually, it is not necessary to to have the locally convex condition here. As it happens, all we actually need is actually we can actually reduce this this theorem. We can reduce this quite substantially, I think. I'm not 100% sure, but the idea is that in line with so up here we had this theorem about triangles, so it's about triangular loops in convex sets, and the essential idea that we used about this was that as we decrease the size of our triangles, the perimeter should decrease. The perimeter should be decreasing as a proportional to well, linearly, really. So here as we decrease the diameter linearly, the perimeter also decreases linearly, and the idea was that as we decrease the diameter and the perimeter, we should also have the distance, so the value of this function f, its difference from its linear approximation, which we had labeled g here somewhere, g. So g is the linear approximation for f, and the idea that we had used was that the difference, if we take this integral, that this difference of this expression here, that this should also be decreasing sublinearly with a diameter. So the idea was that as we decrease the length and the diameter, we should also be decreasing the integral should also be getting smaller sublinearly, and when you combine that, sort of when you compare them, the ratio between the two should actually go to 0. It's sort of like doing the derivative calculation. That's sort of the central idea behind this proof. I think we actually don't need to use triangles for this. We don't need to use a convex set. I think we can do a similar thing just using homotopies. So the method that we had used for this homotope proof is to cut up the input plane into very small tiles, and then to use the fact that the integrals on those tiles vanish to show that when we sum them all up, we just get this difference, and this difference should vanish. Instead of doing that, instead of doing this, and having these be equal to 0, we could instead just find a way to prove that this summation actually vanishes. The way that we could do that is essentially by the same sort of idea. Suppose it doesn't vanish, then we'll try to find like a limit point for these tiles, where these integrals are sort of in a sense too large. If these integrals are too large, that's one possibility. I'm gonna probably come back to this in some other stream, but I just wanted to point that out, that it might be possible to merge this theorem. So we had 3 different theorems about this idea. We went through triangular loops, and then we used that to prove the same thing for general loops in a convex set, and then we used that to prove the general homotopy condition for integration, that homotopic contours have the same integral for a differentiable function. I think it might be possible to merge these. We'll do that at a future date. For now, though, let's attempt to, we'll see if we can prove the theorem that we're going to prove about analyticity. So, the way that we're going to do this, so I haven't done this proof in this way yet. So we can say our theorem will be let f at s to a be analytic at x0 in s, then and analytic at x0 with f prime at x0 is in a star. Then f has an analytic local inverse function near x0. So this is the theorem that we want to try to prove, or something with the essentially the same content, possibly worded differently. So the way that we're going to do this is that we're going to construct the inverse explicitly. So I worked out a formula earlier on paper, and you will see how this formula works. So we'll have to do a little bit of work to actually show that this formula actually converges to something reasonable, that all of this works. But the formula that we'll be using is, we'll say, we'll construct a coefficient series. We'll say let, so we'll say actually take the case that f is, actually we'll just say let a sub n, actually we'll just, yeah, let a be in a n 0, be the coefficients of the Taylor series f of x equals sum on n of a sub n times x minus x0 power n, or something to this effect. So we want to have the a sub n are the coefficients for the Taylor series for f, and then we'll define the coefficients for the inverse. So we'll say let b0 be equal to x0, and actually let's do it this way. Let y0 equal a0, and which is also f at x0, and let we'll have b0 be x0 and b1 be 1 over a sub 1. Then for all n greater than 1 integers, define b sub n inductively using the following formula. So the formula that we need is negative 1 over a sub 1 times the summation, this should be b sub n. B sub n equals times the summation, so we have k equals 2 up to n a sub k and then we have the summation. This one's a little complicated. N in n power k, such that the sum of m is n, and the product from j equals 1 to k of b sub m sub j. I think I wrote that correctly. So this is a very involved formula. So we'll have to expand this a little bit. We'll probably have to write a few lemmas for this. We could also maybe make this a little simpler. So essentially what we want here is, so we have we're doing this inductive definition on b sub n. Actually, let me make sure I got all the variables correct real quick before continuing. Okay, so the idea is that they have -1 over a1. That's fine. This is valid. So just to be clear, a sub 1 is actually f prime at x0. That's just to be clear about that one. A1 is as f prime at x0. So because f prime at x0 is a unit, then we have this this thing. We can take this reciprocal. Okay, so we have this summation across this particular lattice. So this is the set of all. So M is a k length sequence of positive integers, but it has the condition that if you sum up all the entries of that length sequence, it equals n. It just equals n. And then for each one of these terms, the summand of the summation is this product. So product from j equals 1 to k of b sub m sub j. So this does constitute an inductive definition. The reason that this constitutes an inductive definition is this will be considered inductive so long as these m sub j's. So here we have this b. So we have a bunch of other things that we know. So a is determined in advance. And then the only thing we have here that's uncertain is this b, the b sub m sub j. But m sub j, the only time this won't be inductive is if m sub j somehow reaches n or larger. But the sum across all these m's has to be equal to n. There's no way for that to occur unless if one of these m sub j's is n or larger, then the rest of them have to be 0, essentially, or have to be less than or equal to 0, because they sum up to n. One of them is n sub k. They're all positive, but actually they're all greater than 0. So if one of them is n, the rest of them have to be 0. None of them can be 0, so the rest of them have to be well, there can't be any rest of them. So actually, in that case, if any of the m sub j's are equal to n, then we have to have k equal to 1. But that's invalid, so we just have k equals 2. So if k equals 2, and we're summing across this lattice here, and because k is equal to 2, and we're summing across this lattice, there's always going to be at least 2 elements in this m vector, and the sum is n, and they're all positive. So none of them, they're all positive. So none of them can be n. So this would constitute an inductive definition. Once we have all these expressions, then we're going to say define the function g as follows. Define the function g using the power series g of y equals the sum across n. Then we have b sub n of y minus y 0 power n. So this is our explicit construction of the inverse function. I know it definitely looks like I pulled this formula out of nowhere, because I kind of did. But we're gonna see how this is valid. We're gonna need a couple methods. So first of all, we're gonna need a method to sort of get this sum across the lattice in there, and we will find a way to do that. In particular, in a lemma, I think. So we'll do this. I'll start this as a theorem, and then maybe it'll turn into a lemma or something later. So we'll say, let's see, what do we want the most general form of this to be? We have a product of, let's see, sums of similar length. I think all the sums have to have identical lengths. And we can consider, okay, so, and then we'll have a summand, which will be, just call it alpha m n, or we could do f. Actually, yeah, that's fine. Okay, so let m and n be in naturals, and let alpha be in a m times n. Oops. There we go. Then we have the following identity. So we have product n equals 1 to capital N, sum n equals 1 to capital M of alpha sub let's do n comma m and this will be equal to a sum across m in we'll do capital M to the n power of this product, same n equals 1 to n of alpha sub, so we still have n and then m sub n. Something along these lines. Let's see how this looks. Hold on, I left something on. Let me turn that off. So this is what we want to prove. This will sort of support what we're doing for this theorem. So essentially, this just follows from identity theorem, or sorry, not identity theorem, the distributive law, actually, much simpler than identity theorem. So this is essentially sort of the distributive law. So what we have here is each of these m's are in this expression m power n. Actually, what we're expressing with this is actually let's be maybe a little clearer. We can say, oh yeah, let's do this. Okay. something like this. Do you think this is a good notation? I'm actually I have not decided how I want to express this notation. Essentially, we just want to have this sum, the summation, as being summing across, well, this little m is supposed to be across these terms. How do I do words? They're supposed to be summed across these vectors, essentially, where the entries are all these integers, 1 through m, which is, 1 through m. Possibly, actually, I could maybe set this up differently. I could say, let m and n be subsets, instead of saying they are elements in natural. I could say they are subsets. What is this? This is math research, actually. This is math research. We're proving theorems. Actually, this shouldn't be m power little n. This should be m power big N. Yes, so we're gonna prove this little theorem here about the distributive law. If you haven't seen the previous streams on actually our subject, they're all archived on our channel, covering lots of the other theorems about this that we've gone over. It might make a little more sense if you look at those first. Although in a few weeks, I'll also be attempting to sort of compress everything we find into more explanatory videos, if you want to wait for those instead. Okay, this actually, I like the way this looks, and also it makes sense. Except for this product needs to be changed now. Okay, so the proof is, we're going to do it by induction. So we're going to prove this by induction on these sets. I think both. This is LaTeX code, actually. It's used to write. It's what is used to write these sorts of math sort of papers. But yes, it's very math. Yeah, LaTeX is used to write math expressions, math papers. We're very deep in, as you can tell. We're on page 30 of writing this, so we're quite deep in. But this theorem would possibly make sense if you were a little more comfortable with math, but that is going to have to be something you'll have to decide for yourself. Okay, so to prove this, so we're going to do by induction. So I think we're first going to notice that this works in the case of, I think, if our product is I'm not sure about that. Okay, but yes, we're going to observe. So the first thing we want to sort of identify is that this is true in the case where, let's say, we'll do an induction through both m and n, I think. So what we're going to want to do, so in order to set up sort of an induction, we'll want to find a way to turn both of these sort of expressions into one another. So if we start out with this sort of thing, so we can imagine taking out some element. Actually, we can imagine, let's do it this way. We'll have this first expression with our n's, and then we will multiply this by another summation using this sort of inductive definition. And this other summation that we'll be using does not like what I'm doing. Oh, that's why. So this other summation will be, instead of doing m in n, we'll do, instead of doing alpha n m, we'll do, I don't know, we'll do n0 as to sort of set up our induction. So we'll assume like n0 is some element that's not in the capital N set. And this should be, so this is if we just have, let's see. And 0 like this. Oh. Well, good luck to you. I think you almost definitely will not understand for this in 7th grade. You're free to stay and talk. But thanks for stopping by. Okay, so we have, so in order to set up our induction, we're taking, this is 11th grade. I'm not sure if that's true. Okay, so, okay, so we have n, so we're taking n in the set of n union n0. So we're sort of including an extra n0 into the set. And we're rewriting this as, well, if we just have this product, we can just pull out this n0 term, which would be this one. We can then use, so if we're just sort of setting up an induction, this other summation, we would have this right side, and we would still have this here. So we're going to set up as something like this, but we actually don't need these extra parentheses here. So I can pull these out. Let's do it in a line environment. Oops, that's not what I wanted. Okay, so we've got, right, okay. So we're setting up our expression. We have this initial term over here. We're going to pull out one of these terms of the product, and then we're going to use distributive law to essentially pull this in. So this will be alpha and 0. We're going to pull this all the way through to this product. That lets us rewrite this product as, instead of n in n, we have also with the element n0. Okay. We shouldn't use m twice. I think that's something I shouldn't have done. Because now we have this double summation. So let's do this. We'll do a change of variable. So we'll, not here, I think right here. So right over here, instead of doing m, we'll do m sub n0. Okay. Okay, we'll do something like that. Okay, so let's set this up, but let's actually do the sort of description. So we're going to prove this by induction through n for each m, and then we'll have to prove the base case. So actually, we can prove this in the base case of n equals 1. Trivially, if the set size n equals 1. So for each fixed m set, we will prove this by induction across all sets n. Induction in terms of by induction across the cardinalities of all sets n subset to natural. Actually, they don't even need to be finite. Or sorry, they don't need to be sets of integers. Okay, so so we'll do this. Like this. This might glitch out. So we have product n in, and actually we'll say, instead of n, we'll do I. If I and n is the only, actually let's do j. Product n in capital N, sum m in capital M, alpha sub nm is just the sum of m in capital M, alpha sub j m, which is also the sum m in m. Actually, we'll leave it. No, this is fine. n alpha sub j, comma m sub the only element, I guess, m sub j. Wait, does this make sense? Yes, it does. Which is also the sum alpha sub j and then we can have this be the product of n in n on the inside, and just replace j with n. Okay, so in order to prove, so we're going to do this induction across the cardinalities of the sets capital N. So we'll leave the set M as fixed, as just a fixed set. And we're going to take the case, suppose the cardinality of N is 1, then let J be one of the elements in this capital N set. Since all the products are singular, so this left side, that's this one, we have this product N and N, M and M, alpha and M. This product is singular, so this is just M in M of alpha sub Jm. We can also say let M be in M power N, so this is sort of the function set. Since this capital N set has only one element, which is J, then there's just sort of this natural isomorphism, which is M in M power N. This is just the same as just having the same M's, but just replacing M with M sub J. So we've just basically relabeled the elements. And then we have alpha sub j, m sub j. Well, this alpha sub j, m sub j is the only element of n. So this alpha j, m sub j, this is the same as the product across n in n of alpha n, m sub n. So this is sort of this simple case where n, the cardinality of n, is 1. In order to prove the inductive case, so we can say, now for the inductive case, suppose the theorem applies for this set N, and then let J not in N then we shall prove the theorem using the set N union set containing J, singleton set. Yes, so we've proven it in the case that the cardinality of N is 1, and then we're going to prove it in the case, actually we can say, yeah, this is fine. Then we're going to prove it in the inductive case. So suppose it works for the set N. So here we just proved it for a singleton set, for example. Then we can take, actually maybe I'll say finite non-empty sets. Okay. Right. So in order for the inductive case, so we say suppose it works on the set N, then we'll take some element J which is not already in the set N, and we'll prove it for this union and union element J. So we'll start with this product again. So we'll have, instead of N0, we'll do J here because that's a little more compact. Most of this is already written. I'll just have to edit this down a little bit. Okay. Okay, so we have this product. We have the product across N in capital N union the set J, and then this sum of M in M, alpha and M. So this is the same left side of this equation. We're going to pull out this, so out of this product, we're going to pull the J term out. So we have M and M, alpha J M times this summation. We can rewrite this this other term. So this product sum turns to this sum product, and let's get some more parentheses in there still. So this this term here, so we're using our inductive premise to turn it into this. We also want to work with this. So this summation here, we'll do a change of variables. So instead of doing m in capital M, we'll actually do m in m power set containing j. And instead of just doing m, we'll do m sub j. Right, like that. Let me see how that looks. Okay, that's fine. And then we'll essentially just merge these. So we get the sum of m in m power set containing j, sum m in m, and then we have alpha j m sub j. Okay, that lets us sort of merge down this product like this, and then we just have this remaining term should just be like this. And that is pretty much the whole thing. Yes. So it's basically just the distributive law, and it doesn't like this. This is too long. Let's put that on a new line then. Okay. Yes. Okay. Yeah. So essentially, so this base case where the n set, so the dimension is 1. So the dimension is how many sums we're multiplying. So when the dimension set is cardinality 1, then we just essentially these products are singleton, so we can just sort of remove them and then reintroduce them however we want. For the inductive case, so we start out with this product, we pull out this extra term from this product like this. We use our inductive premise on this product of sums to permute them, and then we just do a change of variables just like we had done in this one-dimensional case. We just do this change of variables like this. So we just do this change of variables on this one. We use distributive law, right? So we just have the sum of this thing times these other sums of these other things. So we do distributive law to pull this alpha j mj in. This product reduces down to this product again. So just like how we had pulled out a term from the product, we're putting it back in. And this is valid since this is j mj, and then this is n m sub n. And then we just merge these two summations. So we have the sum m is the j index variable, and then we have these other m's. Actually, right here we want to do a change of variables because we don't use the m variable twice. I forgot about that. So let's do m sub j in m, and we'll do here. Actually, I think that's fine. We'll do m sub j just like that. Let's change that in this previous line as well. Okay, that's good. Yeah, okay. So essentially it's just distributive law that we've done. So we just did the distributive law to find this. So this will be useful for us. We can maybe add a corollary. So the corollary that we can add is we can say, let me think on this one. I think what we want to say is we want to do a we want to have a sequence of dimension sets which are sort of increasing, so we add more and more elements, such that the union of all of them is a infinite set. And once we sort of set it up like that, we want to prove that if we take this dimension to be infinite, that we could also take the dimension to be infinite over here. So we'll do that as a corollary, and we'll have to specify the conditions on when that will be true. So we'll say let m and let n be a finite set and n be a countable set. Such that, and we want to say, actually we'll say m be a countable set and n be a countable set, and let, so alpha again is in a n times m, and be a finite set, n is a countable set, alpha be these coefficients, such that, and we want to specify that the summation converges very quickly. So we want to have, I think, absolute convergence. So this will be, if we're limiting through these, oh no, wait. Let's do, actually we'll do an easier version. We'll limit through the m sets. We'll say let n be a finite set and m be a countable set. Yes. And let alpha be these things. Such that, and we'll say the sum across m and m to the n product alpha and m converges absolutely. Actually, we'll, let's reframe this. Okay, so we'll frame it like this. So we'll frame it like this. So we'll say let n be a finite set and m be a countable set. So this is a improvement. So before we only had finite non-empty sets. Let's be a little bit more specific. A non-empty finite non-empty set. Whoops. Okay. Okay, yes. So as long as the sum of products converges absolutely, we want to say that this will still apply. So the way that we'll do this is we'll say so we'll say, okay, since n, since m is countable, we can rewrite, oh wait, actually this doesn't make sense. This set will be too large, I think. If m is countably infinite, no, maybe this is fine. It needs to be, it's not enough for these to be, actually, let me double check. Maybe we don't need to do this. Hold on, we have... No, we do. Okay. We don't need this full expression, I think. It needs to be such that the products have to actually make sense. So if we have an arbitrary sequence like m in m power n, and we're multiplying infinitely many of these terms, alpha and m, we need it to be such that these products tend to 0 quite quickly. We could also, oh, let's see, we could, instead of doing this, we could actually just make the limits as implicit. Or sorry, explicit, pulling the limits out. So here we're sort of doing, if we have an infinite base here, we're sort of doing an implicit limit by limiting, because we have this infinite set m power n. We're sort of doing an implicit limit here. And that, maybe actually this might work anyway. We could maybe readapt this proof. So let's think. So because we have the dimension being finite, we can say, well, even if this m is converging absolutely, so this proof would still follow for the case of 1. And we also have, if we do this general product of sums, let's say, okay, I know what we can do. We can say so long as each of these summations converge absolutely. I think that's what we can do. Because then we'll end up with this summation and this product of sums. And then we still do this inductive premise. This change of variable is still valid. And then we just have the distributive law. And pulling in, merging these two sums is justified by, I think, absolute convergence. I want to say that that will hold. Okay, I think I know what we need to do if we want to merge these. So we're going to need to prove that if we have two summations which converge absolutely, then their product will also converge absolutely. I think we can maybe do that. So let's see if we can do that. we can say let A and B be countably infinite sets, and let alpha be in AA and beta be in AB. Be absolutely summable. Then we have the sum. We have I in, let's do A in A, alpha sub A, and sum B in B, beta sub B. Okay, multiply these. This will just be the summation across, we'll do C in A times B of A sub C sub 1 times B sub C sub 2. Very strange proofs. These are definitely going in an appendix. They're very, very cluttery. Okay, let's see if we can do it like this. Oh, we can also do ordered pairs. Okay, let's try this. So in order to prove this, we want to say, okay, we want to say that we can do this. So we want these to be absolutely summable. So actually, I think this is actually really straightforward. So we can just say, since we have, actually, wait, let me think on that. I'm trying to think on if we can actually do this. In the case of, I think in real numbers, this is definitely true. So long as both, for example, so long as both A and B are sufficiently large, then eventually alpha and beta will be less than 1 in magnitude. actually for complex numbers as well, will be less than 1 in magnitude. And as you sum them up, you can just prove that that the summation of the absolute values converges by bounding okay, I got it. Okay, since these sums alpha, beta, sums of alpha, beta are absolutely convergent, we have the following convergent sum, and that sum is, we have the sum due sum of A in A, alpha sub A, actually sorry, not alpha, we'll do absolute value alpha A, and then we have exactly the same thing except with B and beta. And instead of, so we'll just do, we'll keep this A and A sum first. And this B and B sum second. But we will do distributive law to pull this A alpha A inside okay. And then we just use submultiplicativity of the A function. And I think that's all we need. Let's make this also a little clearer. Okay. Okay, so we have this. This is fine. Using this, we can rewrite this theorem to actually merge this corollary. Okay, so we'll say only empty sets with n finite and m countably infinite, and alpha in this. And the previous theorem applies when, and we just need converges absolutely for every n m. Okay. It's exactly the same statement. Okay. M and M be finding non-empty sets, and alpha be these coefficients. So in this case, so this one follows from the distributive law. This corollary is going to follow from this lemma, essentially. We're going to say let A and B be countably infinite sets. We can maybe put this actually below. Okay. Okay, so we have the same theorem, except we have countably infinite, and each of these summations converge absolutely. And our justification is we use the same proof as before, and to justify the last line of the proof by absolute convergence. So same proof. So it's so we're saying just apply the same proof and justify the last line by absolute convergence. So this last line is this one. So all of these. So this initial condition, this initial step follows. So these products are singular. So we're not really doing anything by. So just by removing this product, essentially we're expanding the product in this first step, which does nothing, and then we're reintroducing it on the inside, which also does nothing. In this, in the inductive step, so we're saying start with this product, extract this first term, that's always valid, because it's just a finite product. Then we have this sum times this thing. We use our inductive premise to swap these sum and product. Then we use distributive law to pull out these alpha into here and merge this into this product. We can actually maybe make this a bit easier even, and just say that when we use distributive law, we just merge this into the product right away. Yes. And then this last line, merging these two sums into this singular lattice, is justified by absolute convergence. So we have this theorem here. So if we have two infinite states A and B, or two countable sets A and B, such that their summation converges absolutely of these alpha and beta, then we can merge their product like this, and this will also converge absolutely. And that's exactly what we're doing right here. So we just have these two summations, and we just converge. We combine their convergent sums into another absolutely convergent sum. Yes. I'm trying to think on if we should rephrase this to make it more familiar. I think this is fine. This is probably fine. So this is sort of this is what we'll use to support this theorem to produce our analytic function. So we have this result, which is actually this corollary is the important one. If we have a bunch of summations which converge absolutely, then we can swap the sum and the product into this lattice, and this will also converge absolutely. Yes, and this will also converge absolutely, and that's essentially all we need. We'll maybe move these into an appendix, but we'll leave them here just for now. Okay, so using these now, actually we can justify where this whole nasty expression comes from. So we'll say in order to, so we'll say let A be the coefficients of the Taylor series for fx, blah blah, and y0. Okay, and then we'll say let y0 be these, and so on. In order to justify this, we need a formula for an explicit formula for composition of power series. So the way to do that is so we'll produce the inverse function explicitly by creating a constructive formula for the composition power series, and find, so we'll say let f and g be power series centered at x0, y0 respectively, and with coefficients alpha and beta in A and 0 respectively, and with a positive radius of convergence. Both with a positive radius of convergence. Okay. Let's give some space here so I can see what I'm doing. Okay, so we're going to say let f and g be power series centered at x0 and y0, and using coefficients alpha, beta respectively, both with positive radius of convergence. Then we're just going to calculate their composition. So the way we're going to do this, so we'll say f of g of x is going to be equal to, so we'll do a summation, we'll do n in n0, and then we'll have alpha sub n times, we have negative x0, actually we'll just do g of, actually we'll make it a little easier on ourselves. We'll say that the power series for g is centered at, okay, yeah. Power series for G is centered at f of x0, so that, actually we'll just say y0 because f is just f of x0. Yes, I think that's all we need. Okay, so we'll assume power series for G is centered at y0 equals f of x0. Then we have f at g of x, so we have the summation. Actually, we'll do f of g of y. F of g of y minus x0 And this is, so we just have the summation, we have n in naturals, n0. We have alpha sub n, and we're multiplying this by, so we have negative x0, is this what we want to do? Let me think. Okay, so we're just going to assume that the center points are all 0, that the input and output center points are 0. Okay, so we have f at g of y is, okay, so we have the summation and natural alpha. So actually, instead of doing n in natural, because our first f0 is 0, we can just do n in naturals. Actually, we'll just do explicitly alpha 0, beta 0. Okay, so we'll do f gy, sum natural alpha n, gy minus, and we actually don't need gy, so we just have minus x0. I mean, we just have gy power n, and then we can expand this, so we have alpha n times, so we have g of y power n, so this will be, g of y will be the summation m in naturals, we have beta sub m, and then we have y power m, and this is all being raised to the power of n. Okay, yes. So we're doing all of this, and then we can further rewrite this as, so the same thing, except our product, or sorry, our power n is actually going to be a product. We'll do product j equals 1 up to n of just this expression, just like this. Okay, and then we need to know that these will converge absolutely. So we have a sum of products, and we know, so this is the composition f of g of y. So we're going to use this corollary here. So if we have actually, oh, this is what it is. We have this product of this summation. So actually, let's remove these parentheses so that's more clear. Okay, and then we can say, since FG are analytic, so too is their composition. So we have, or actually we can say, so each of the sums, or rather, for y close enough to 0, all the summations of, or rather, yes, the summation sum m beta m y power m will converge absolutely. Actually, we don't even need this. We can say, since G is analytic, for all y close enough to 0, the summation will converge absolutely. So we can can premute the sum and the product. So we still have this f of g of y. So we're going to permute this very last summation with the product. So we just swap the product around, and instead of summing m over naturals, this will be summed over naturals power n, and we will get, instead of just m, we have m sub j. Actually, we'll say, let's make this easier, and we can just put this all right in the same place. Okay, so we're gonna leave ourselves right there. That's not good. Okay, so the swapping of the sum and the product is valid since G is analytic, so the summation converges absolutely. So we just swap the sum and product around, these last two, just like we did in our just like we had done in our in our previous theorem about swapping sums and products. Once we have this, we can, okay, so what do we want to do next? I think we want to in natural power n. Okay, so we'll say for each m in, we'll say natural power n. This shouldn't be an n0 either. Let's fix that everywhere that we have it. Okay. Okay. So for each m in natural power n, let capital sigma of m be defined as m1 plus m2 all the way up to m sub n. We can then, actually we can say, since our summation converges our rightmost summation converges absolutely, we can rearrange the summation by partitioning it across, by partitioning it in terms of sigma m. So we have f of g of y still, and this will be okay, so we have f of g of y, we have the summation, and a natural alpha n, so on and so forth. Okay, so this summation will do a sum across k equals n up to infinity, I guess, and we'll limit the summation across capital sigma of m equaling k. Okay, so this since this summation converges absolutely, each of these summations converge absolutely. When we permute the sum and the product, this will also converge absolutely. So this summation here converges absolutely. Since this converges absolutely, we can rearrange it. So we're going to rearrange it in terms of this capital sigma function. So we'll say we'll have a capital sigma of m is just defined as the sum m1 plus m2 and so on up to m sub n. And so we're saying since this sum converges, this one, absolutely, we can split this up. So we'll split this up using k. So k will run from n up to infinity, and we'll split this in terms of each m in this lattice. We'll split it up in terms of this summation sigma m equaling k. So each m in this lattice has to have a sigma value. Actually, we can say, well, let's be a little more explicit. Since each m sub j is greater than 0, which means greater than or equal to 1, then sigma m is greater than or equal to n. Okay, yes, so instead of just having this sum across all of these points, we're going to partition it using this sigma function. So each of these sigmas has to be an integer. It'll be greater than or equal to n, since there's n terms and each one of them is at least 1. So we split this up, so we have this summation, and then we have this smaller summation. And then the last thing we want to do is I want to permute this sum of these alphas. Actually, let's change these alpha sums as n equals 1 to infinity, since this is going to end up being more useful. Okay, so we've done the composition, we've permuted the sum and the product, we've then partitioned this sum into how much what each of these vectors add up to. We're then going to say, well, we have this product, right? This product of beta sub m sub j times y m sub j. Well, this is just this y m sub j. This can actually be pulled out as we have this y m sub j. This can be pulled out of this product as y of y power sigma m, which is k. And then we can pull that, this sigma k, this will just be k, and we pull this y power k all the way over to this k summation. Let me fix that. Okay, yes. So we've done the composition, we've swapped the sum and the product, we've partitioned the new sum, and then we've used this partition to pull out this y power. So each of these partitions is saying we'll take these vectors where all these m's add up to k. We're just multiplying through powers of y. So this will give us y power sigma m, but by our partition sigma m is k. And that just pulls out as y power k. And then we can swap these. So I'll pull through this alpha sub n. Through here. And then all we need is actually to swap these two summations. I want to make sure it's clear that this is justified. So we're about to swap these. Actually, I'll do the swap now. Instead of doing n equals 1 to infinity. So this is k greater than or equal to n. It's so equivalently n is less than or equal to k. Okay, so we end up like this. So this is actually quite nice. So this is an explicit, so this is, by the way, this is exactly where we get this whole mess. Right here. That's where all of that comes from. Let me double check my notes on this. Okay. Okay, so this is sort of our explicit representation of the composition. So this is actually as a power series. So we have f of g of y, and we end up with a power series representation, y power k of this whole summation. And this is the only place where our y power k's are. I think what's nice actually about this is that this whole tail term is now finite. This is for each fixed k, this is a finite sum of alphas. This is well, we can prove that this lattice with this restriction is also finite, and then this is a finite product. So actually, this whole mess here is actually a finite operation, which I think is actually quite nice. So this is our representation, our explicit representation for the composition. Okay, so. What I want us to do now that we have this is I want to extract, essentially I want to do this in reverse. Okay, so okay. Yes, okay. So I'll make this note. So again, or sorry. Okay, so we've constructed this. So to recap on this, we've done the composition. We swapped the sum and the product. We've partitioned this summation in order to extract these y's, and then we've swapped these two summations in order to pull this through. This is still valid. So again, this entire summation converges absolutely. And this whole summation had converged absolutely in the beginning as well. So I believe, at the very least, especially if we had gone through justifying these expressions. These would probably be fine. What we can do now is we can say we can actually use this in sort of an inductive definition now. So we'll say okay, so this formula allows us to construct an explicit inverse function for f. So we'll say so this lets us construct an explicit inverse function g for the function f. So we'll say let's check. Okay, so we'll say let b0 be x0 and b1 be 1 over a1. And for all n greater than 1 integers, define b sub n inductively using the following formula. And then we have this formula. Let me make sure that this this checks out. So this is roughly what we had. Oh, nice. We ended up with the other indexing scheme. Let me just swap these real quick. Okay, N, K, N, and J. Instead of n, we'll do k. We don't want to do b, actually. We want to do alpha and beta. Okay. Okay, so so this is now our sort of definition. So the first thing we have to do is this part here shows that if we have functions f and g which are analytic, then this is what their composition will be. This little expression here is essentially reverse engineering these coefficients to force their composition to be a linear function, which is the identity, in fact. The only problem is that using this as a definition rather than just using the composition, this doesn't actually guarantee that these coefficients will grow sufficiently slowly. In order to do that, we can do that though. We can do that. The way to do that though is the way to do that is complicated, to say the least. We're going to have to verify that we can find an upper bound on the beta coefficients, which is small enough to still have a positive radius of convergence. And then when we compose them, just given that we defined beta using these, when we compose them, this will just end up being exactly what we need it to be. So we'll need to do it like, okay, I think I know what you need to do. So we can say, actually, well, technically every power series converges in a dense set, but not necessarily with positive radius. So now that if G has a positive radius of convergence, then the composition f of G of y equals y for all y in a neighborhood of 0. So the way that we justify this, so we just have the composition, so we have f of G of y is equal to this whole mess. So we have k equals 1. So we'll do this whole summation will be, actually let's get these labels. We'll do y power k, gamma sub k, why not? We'll do gamma sub 1 is equal to, so this is 1, k is 1, so sum from 1 to 1, summation equals 1, and this just sort of breaks down to, we get alpha sub 1 times this whole mass. We have actually just beta sub 1 actually, which is just 1. And then we also have there's this, then we have gamma 1, and then we'll also do gamma sub k for all larger k. So the way that we do that is for k greater than 1, we have, we'll actually just extract out the n equals 1 term. So we'll do n equals 2, have this whole summation, and then this sum would be when n equals 1. So n equals 1, n equals 1, and k is k. So because m is in n1 and sigma k, then actually m equals k. M equals k, so m sub j would be k. We have this n, again, is 1. This product goes away. And this summation also goes away. And then we just have alpha 1, sum m equals k. This goes away as well. But this is exactly what we had. So we just had our definition of beta sub k would be that. So we can actually be just align these. Oh gosh. Yes, okay. So, so you have the summation. So, this is the composition as the formula. So we're saying, so now that we have this composition formula, we're saying, define, instead of just having G be arbitrary, we're going to define G. So define beta is 0, 0, beta 1 is 1 over alpha, this should be alpha, 1 over alpha 1. And for all integers k greater than 1, we define beta sub k inductively using this definition. And then we just define g using, they should be beta again, using beta as the coefficients. Then we say, so first we're going to do, we're going to identify if it happens that g has a positive radius of convergence, then this composition f of g of y equals y for all y in a neighborhood of 0. And this is demonstrated with this. So if we assume that g has a positive radius of convergence, we can just use the composition formula. And then we just note, so if this is our composition with our coefficients for the composition, we're just going to let these coefficients be gamma, so we don't have to type it over and over. So this is gamma. We're noting, well, gamma 1, if we just evaluate all this, so each of these are finite operations, so we can just expand these. So if we do gamma 1, this just reduces to alpha 1 beta 1, but beta 1 was defined as being 1 over alpha 1, so this is 1. So this is 1. And then for any k greater than 1, our gamma k is, we just take the whole definition for gamma, which is this whole mess. We just extract the n equals 1 term, which ends up being alpha 1 beta k. We just extract that n equals 1 term, and we're just left with this whole summation. But this summation, right, this is just beta k times alpha 1. This is negative beta k times alpha 1. Just like this. It's exactly the same expression, just copy pasted. So because we have gamma 1 is 1, and all the larger gamma k's are 0, then f of g of y is just y. It's just y straight up, and that's it. So if g has a positive radius of convergence, then this will be true. In order to prove that it has a positive radius of convergence, so now we have to prove that. So then we can say, actually we'll say, moreover, since f, g, r both have f prime at 0 and g prime at 0 are in A star, then they are both locally injective. So f, g are local inverse functions, which would prove the theorem. To justify the conclusion, we just need to prove that G does have a positive radius of convergence. Yes, so to complete the theorem, we just have to prove that actually, yes, G does have a positive radius of convergence. Also, I might take all of this portion of the proof and put this maybe in the power series section. Actually, this would be the most useful, because this is actually this is quite straightforward. I think it could definitely be put there. Okay. Anyway, so all we have to do is verify. So we have to verify that these coefficients have a positive, induce a positive radius of convergence. And the way that we can do that actually is just by putting an upper bound on them. So first we're going to say, we'll say define some coefficients delta sub n. Actually, we'll do delta. Yeah, we'll do delta sub k inductively in a similar way to beta, except using delta 1 is a of 1 over alpha 1. Okay, and we'll have for k greater than 1 also, so we can use the exact same definition, but we're just going to use the absolute value. Actually, let's do it this way. We'll do delta 1 is 1, and we'll do a of alpha n. Okay, so this is the same, this is essentially the same, oh, sorry, that shouldn't be beta, that should be delta. Doesn't delta have another? No, I guess not. Maybe I'm thinking of sigma. Yeah, look at that. Okay. Actually, let's do... Yeah, we will do this. Okay, so essentially all we're doing, there should be subscript. All we're doing is we're defining these deltas to be, instead of just being instead of just being the definition for beta with just these alphas, we're going to do essentially the same thing, but we're using the absolute values of alpha. So this is actually really useful. So for any this is useful because for any k we have a of delta k as being greater than or equal to a of beta sub k. So basically by taking all of our alphas to be positive, and then also just making all of our deltas positive as well, this just ends up being larger than beta. This can be proven inductively. This can be proven inductively. Essentially, it's just it's just using the subadditivity and submultiplicativity of our absolute value a function. That we just have these right here. We just have this alpha 1, this sum, and then this product. And so when we apply a to this beta k, this pulls all the way through. So if all the earlier deltas are larger, actually hold on a second. Yeah, because all the deltas are positive and larger, actually, is how that is. But yes, just by using the submultiplicativity of the a function and the subadditivity of the a function, we do get that when we apply this all the way through, because our deltas are larger and positive, it just ends up being larger overall. Yes, than our betas. So we do have this as being this. So then all we have to do is prove that the phi value of the delta sequence is finite. So how can we do that? So we can do, let's think on this. So I want to prove, I think it's, let me think on this for a second. So I think what we want to do is we will use the fact, so we're doing this sort of summation here. I think what we can do is we will say, we'll put a rather extreme bound on the alphas, so we'll find some coefficients, some coefficient to bound the alpha sequence, and then essentially we just want to show that we can bound the deltas using that sequence. So let's think. So I believe this summation here, I believe that the domain is polynomial in n, n and k. It's like a binomial coefficient. Actually, specifically, it's we have k things. M is all positive terms. They add up to k, and there are n of them. So n things adding up to k. This is like the stars and bars problems from combinatorics. Since they all have to be positive, I think we can just say there are, instead of doing k stars, we can do k minus n stars and still n bars. So there are should be in any fashion. So there are k objects, and n r bars. So I think this is it k choose n? I think. I feel like that's not right. It might be k choose n. Actually, yes. I think it is k choose n. Okay. So I think this set is k choose n size. We can compare these alphas to using our phi characterization. So we can say find any, take any phi greater than capital Phi of alpha, and let A be such that I can do in A sub real be such that we have A of, oh, we can actually maybe find an if we do it this way, we can maybe find an explicit representation. Okay, such that A alpha n is below phi power n, A times phi power n. Okay. Actually, let's also do, no, this is fine. Okay, so phi greater than this, and let be such that this is, okay. Now define the sequence delta k in some way to beta. So after using delta 1 as the absolute value of, actually want to do, instead of alpha 1, we'll just do A. Oops, I accidentally cut it off. And instead of using A of alpha, where is it? Instead of using A of 1 over alpha 1, we actually want to use, instead of A, it'll be actually, yeah, this is fine. Delta 1 is, okay, I'll also use that. But instead of here, we'll use A phi power n. Okay, here's the part I haven't done yet. Now we have to prove that this whole expression reduces to something kind of nice. Okay, so each time we go through this process, we're going to be adding up some products. If we want to try to factor these, each delta will have a certain number of these factors of A alpha 1. Actually, let's do it this other way. If we have our function f, we can actually just calculate the inverse function. F of x is a summation n equals 1 to infinity. We have a phi n. Actually, this is a little different, isn't it? I wonder if we can maybe just sum these is what I'm thinking. I'm thinking maybe if we can prove that if we can add these up in a geometric sum. Actually, that could maybe prove it. But I'm not sure how we would do that. I think what we want to do is actually, yes, let's do okay. What we can do is we can set these up so that when if we do a summation again, because it's inductive though. Actually, that's maybe okay. I'm just trying to figure out how we're going to bound these. I think we just have to maybe do it directly. Like, for example, maybe we can, so we do get this a 1 over alpha 1. We have this other a here. So we're going to gain one of these factors each time we do this calculation. We have a bunch of real coefficients and then some summations. So just a linear combination of this product, of these different products. This, okay, I know what we need to. We're going to have some, I think, we're going to have some, we can bound this with some real number times this a alpha 1 times this a to the power of summation is k. Let's going through all of these to the power of k, I think. Okay, yeah. But actually, we're going to want here. So, okay. So we'll say, actually, so blah, blah, so on and so on and so forth. Okay, so we're doing the same thing. So we find our phi greater than phi alpha, and we bound these alpha n's using a phi n. But we can increase this a term if we would like. What we're going to do is we're actually just going to assume that a is preceding is succeeding 1. So if it's not as big as 1, we'll just make it bigger to match, and that's still fine. That'll still hold. Okay, so we'll do that, and this lets us, instead of doing delta 1 is a alpha 1 over alpha 1, we'll actually say delta 1 is a of 1 over alpha 1 times lowercase a, and then we'll use this definition. So we're going to do these products, and so what we're going to end up with, I'm not sure exactly what coefficients we'll have, but what we'll end up with is, I think we'll end up with each delta k will end up being absolute value 1 over alpha 1 times a all to the power of k times some fixed number, which I don't know what it'll be, which will be a real number. C sub k is in. Okay, so we can make this even simpler. Instead of doing delta like this, we will do actually, we could say no, that won't work. Okay. Okay, so we're going to pull out, so I want to say that this is going to be some real number times a times absolute value 1 over alpha. In order to prove that, we're gonna define another sequence using a really similar definition, except we just won't have this. And we'll use, instead of delta, you'll see. Okay. That's a lot of errors. Oh, it's right here. What's a lot? Wait, when did I say 5? I totally forgot. Wow, this is a whole bunch. Okay. Okay, so we have ck equals 1. K greater than 1, we define this. So we're going to do c instead of delta. And we were saying we should have ck times these things is greater than or equal to, is bounded above, or sorry, below by absolute value of beta k. So this is true when k equals 1, since absolute value of beta k, this is just 1 over alpha 1. This is bounded by c1 times a of 1 over alpha 1 times a, since a is larger than 1 and c1 equals 1. Then inductively across k equals 1, we just use this definition. Okay, so this is bounded by a left, get rid of this minus, right, and then we have a of alpha sub n, which is bounded by a phi power n, we're actually going to get, so we're going to get n factors, which is going to be, oh gosh. No. We're going to get k factors, and then we'll get one more, which will give us k plus however many the previous one had. Oh, geez. Hold on. I'm actually trying to figure out how many factors we're going to get. Because it's not one, I think. Yeah, so, okay. So if the first one has 1, the next one will have... So all of these, when we sum up all of these k's, when sum m equals k, it'll be... all of our previous ones will have 1 power. So when k equals 1, we'll have 1. When we get up to I think this is maybe isn't gonna work the way I want it to. So if k is 2, then the number of factors we get is going to, so we have this n equals 2, constant, we'll get some real coefficient, that's the phi. We'll have a lattice across n squared such that the summation is 2. So I think the only one available is 1, 1, which will give us how many factors? 2 of them, and then we increase 2 of them, and then we increase another 1. 3. And then when we get up to k equals 2, we will have our lattice, our n will go from 2 up to, so the ways to sum up more than one thing up to k using positive integers, and our k is now, sorry, this one was 2, this one is now 3. Our k is 3. So we could do 1, 1, 1 or 1, 2, which would give us 3 or 4, so we get 4 and then we get 5. And then the next one would be k equals 4. So if they sum up to 4, we could do 3, 1, which would give us 6, or we could do 2, 2, which would also give us 6, or we could do 2, 1, 1, which would be 5, or 1, 1, 1, 1, which would be 4, so we get 6. Wait, is that correct? And then one more is 7. Okay, I think I know how this is going. This is actually an extremely hard problem, as it turns out. I think that this is doable. If we have 5, let's sum up to 5, Four and 1 would give 8, which would increase to 9. Or we could do or we could do 3 and 2, 6, 7, 8, which would also be 9. Or we could do 3 and 1, 1, 6, 7, which would be 8. Or we can do 2, 2, and 1, which would be 8. Okay, so it's 9. Okay, I've got to figure it out. It's 2k minus 1? That was a nightmare to figure out. Okay. So actually what we want is we're going to have a alpha 1 times a, instead of to the k, it's actually going to be power 2k minus 1. Yeah. This is actually a whole lot in one theorem. Wow. Maybe there's a better way to explicitly figure this out, this summation like this, or a recurrence relation. I'm not 100% sure. This will still work though. We'll just have a actually, this is really interesting. Anyway, this should still work. It's just very interesting. Now I have to figure out how we're going to add up all these. What if I did, hold on. I can do no, maybe that won't work. Let's calculate this. Actually, I want to see what this is. Okay, so we'll do n from 2 to the k, 5 power n times some. Oh wait, I can't. Maxima won't do this. Or I can bound CK with a summation if instead of doing phi power n, if I assume phi is greater than 1, then I can bound this by just having k times phi power k. Oh no, actually that won't work at all, because then we'll end up with a factorial. As we multiply through k's over and over again. Maybe there's a non-inductive. No, that's not going to work either, because that's just going to be a nightmare. Okay, I think the problem I'm having is that bounding the alpha coefficients does not really seem to, like on this, I don't know how to simplify this, so I think the cardinality of this domain of the summation is k choose n. If that is the case, we can also maybe assume if we were to make the assumption that our product is largest, for example, oh wait a minute, oh gosh. Okay, I'm not sure. Yeah. I will think about this one more. So this is the part that I didn't do. We could always resort to you know, this whole mess. I really don't want to do that. All of this, not this one. This is always an option, though. Is always an option. But yeah, I think I will just have to think on this one a little longer. So I will stop us here for today. Thank you for joining me. We're getting into a lot of improvements that I hadn't done in my previous draft, which is nice, because this is sort of what I guess the real proofwriting process is like usually. It's just a lot of not knowing what to do for how to improve things. But we'll stop there for today. But yes, thank you for joining me, and I hope you had a little bit of fun and maybe learned a little bit. Today was a little slower than the previous days, but hopefully we did get some done. We did this. That was nice. Swapping sums and products. That's a very useful one. Yes. But I will think on this one, and I think we will be back. If not tomorrow, then the next day, and I will try to come up with a way to go forward on this. I'll just have to meditate on this nightmare approximation, and we'll see what we can do. Okay, well, thank you very much. I will see you next time, and goodbye.